Hi class, in this presentation we are going to be focusing on the adrenal glands. The adrenal gland is really a two-in-one. It's a twofer. We have the medulla and the cortex. They're connected to each other, but they're very distinct from each other. So as you focus on the medulla, the inner part or the middle of the adrenal gland, it's about 10 to 20% of the total volume of the gland. And if we look at this figure, we can see the adrenal right there, the medulla of the adrenal gland right there in the middle, and then the cortex is around the outer circumference. As we look at the adrenal medulla, we are going to find that this adrenal medulla is going to have a dual nature. It's both an endocrine gland and it's a gland of the sympathetic nervous system. So what do we mean by that? It's going to be triggered by both the sympathetic nervous system, the nervous system, and the endocrine system. It's going to have a lot of sympathetic postganglionic neurons of the sympathetic nervous system. And I know we haven't talked about the sympathetic nervous system yet. We skipped the nervous system entirely to cover the endocrine system before we got to, as we're doing this presentation. So let's briefly talk about the sympathetic nervous system. Our sympathetic nervous system is the branch of the nervous system associated with stress response, the fight or flight response. Whenever we're stressed out, and we're feeling on edge, we are going to have activation, or scared, we're going to have activation of the sympathetic nervous system. So within the adrenal medulla, we're going to have sympathetic postganglionic neurons called chromaffin cells. These cells are going to release stress hormones, epinephrine and norepinephrine, also known as adrenaline and noradrenaline. The group, or the generic name that refers to both of these, is the catecholamines. These are hormones that are going to upregulate metabolic activity in the bodies. We're also going to have a very small amount of dopamine being released from the adrenal medulla into the bloodstream. Now, within these, as we look at these catecholamines, the adrenaline and noradrenaline in our bodies, there's lots of effects. We're going to have increased physical activity, or the preparation for increased physical activity. It's the fight or flight response. We need to get ready to have a fight physically or to run away physically. So we're going to mobilize high energy fuel sources like carbohydrates. They're going to be dumped into the bloodstream. We're going to have glycogen lysis in the liver. The liver is going to glycogen molecules, chop it up into glucose, and dump those glucose into the bloodstream. We'll have gluconeogenesis in the liver as well. Think back to when we talked about the carbohydrate metabolism with chapter 26. Gluconeogenesis is when we make new glucose molecules. So genesis means to create, neo means new. What are we making new? What are we making? We're making new glucose molecules, gluconeogenesis. Typically, we're making glucose from fat or amino acids. So as we have more fuel dumped into the bloodstream, we're getting ready for that physical activity. Epinephrine is going to inhibit insulin secretion. Insulin is a hormone that lowers blood glucose concentrations. So if we have less insulin in the bloodstream, we'll have more glucose in the bloodstream as a result. And then as we're looking at the results of epinephrine, epinephrine is going to focus on muscles using fatty acids for a fuel source, so that we have as much sugar as possible for our brains. It's worth emphasizing that this epinephrine will mobilize fatty acids into the bloodstream, so they can be used by muscles. If we think of stress responses, if we're constantly being stressed out, we're constantly dumping extra fatty acids into our bloodstream. And if we're stressed out and not pairing that stress with physical exercise, those fatty acids build up in the bloodstream. Being constantly stressed out is not good for our bodies. So if you're feeling anxious, if you're having some anxiety, some stress, a really good thing is to go get some physical activity. Go for a walk, go for a jog, just walk and talk about whatever it is that is stressing you out. That's going to be a good thing for you both psychologically and physiologically. Other things that happen in response to epinephrine is that we're going to have an increase in blood pressure, so that we can move blood quickly. We'll have an increase in heart rate, blood flow to muscles. We'll have more air going in and out of our bodies. Our basal metabolic rate increases. Epinephrine gets us ready for that fight and flight response. Consequently, when we're in a fight and flight situation, we don't need to have a lot of digestion or urine production. Epinephrine downregulates the digestive and urinary systems because those aren't essential to having the fight or flight response. Let's move on to the adrenal cortex. Our adrenal cortex is around the outer circumference of the adrenal gland. It makes up the majority of the volume of the adrenal gland. Oh, excuse me. It's really early in the morning for me right now. I've been up since like 4:45. Anyways, I digress. So as we're looking at the adrenal cortex, it's broken up into 3 layers. We have from superficial to deep, the zona glomerulosa, zona fasciculata, and the zona reticularis. These 3 layers combined make up the cortex. Surrounding the cortex, we just have the connective tissue capsule, and then deep to the cortex, we have the adrenal medulla. Let's look at the names and associate the names with the tissue arrangements within these different layers. When we think of the zona glomerulosa, we're going to have rounded clusters, rounded groupings of cells. It almost looks like they are glommed together in the glomerulosa. As you look at the histology of the zona glomerulosa. And the zona glomerulosa is going to function primarily to release mineralocorticoids. Mineralocorticoids are a category of chemicals that help to regulate the electrolytes, the ions in our bodies. So if we regulate the ions in our bodies, we are going to regulate vicariously, or as a secondary response, we'll regulate our body's fluid balance as we regulate the amount of salts that are in our body. As we look at the zona fasciculata, the cells within the zona fasciculata are going to be in, let me switch colors here for us to bright green. So as we look at those cells within the zona fasciculata, they are going to be bunched together in a structure that kind of resembles the fascicles of skeletal muscles. So if we have these elongated tubes or elongated rows of cells, that's going to be, from a histology perspective, the big red flag that you should look for, the big clue you should look for that you're working with the zona fasciculata. These cells are going to release both glucocorticoids and androgens. And when we think of glucocorticoids, these are going to be chemicals or hormones that regulate glucose concentrations in the bloodstream. When we think of androgens, these are going to be sex hormones. So in particular, when we think of the zona fasciculata, we're going to have a little bit of estrogen, a little bit of progesterone, and a little bit of testosterone. And as we look at females, particularly postmenopausal females, the zona fasciculata of the adrenal cortex is the primary source of estrogen and testosterone in the woman's postmenopausal body after the ovaries have shut down. We also have zona reticularis. The zona reticularis resembles the structure of reticular connective tissue, or the reticular loose connective tissues, I should say. So there's going to be kind of fibers of cells and an arrangement of cells that's going to be very random. There's going to be many threads of cells going in many different directions within the zona reticularis. There's a very branching appearance to those cells. And as we look at the zona reticularis, it's going to release glucocorticoids and more sex steroids. So this is another source of those sex hormones in postmenopausal women. These are also, the zona fasciculata and reticularis are also a source of sex hormones in prepubescent individuals that are pre-puberty. And these hormones that are being released, these androgens and sex hormones that are released from the adrenal cortex pre-puberty, help get those concentrations up to the level that needed to initiate puberty in both males and females. So as we're looking at these layers of the cortex, here's some actual histology. So as we're looking at the zona glomerulosa, we have lots of rounded structures within the zona glomerulosa. As we're looking at the fasciculata, you can see more of a chain or a long string appearance. And then as we look at the zona reticularis, we're going to notice that the cells are oriented in many different directions. They branch in many different directions as we look at the cell-to-cell arrangements. So as we look at mineralocorticoids that come from this zona glomerulosa, they regulate electrolyte balance. The single most important mineralocorticoid is aldosterone. It's going to make us retain sodium in our bodies and excrete potassium. If we retain sodium in our bodies, we are then going to have more water retained via osmosis. So when we release aldosterone, Ultimately, we are going to have more fluid, more water kept in our bloodstream, and blood pressure will go up in response to an increase in blood volume. Aldosterone is a key hormone that is part of the renin-angiotensin-aldosterone system, sometimes referred to as the RAA or the RAAS, the RAS. We'll talk more about that renin-angiotensin-aldosterone system when we get to the urinary system. We'll talk about that in much more detail at that point in time. We also have glucocorticoids. Glucocorticoids are hormones that are going to control glucose concentrations in the body. They're going to be released by both the zona fasciculata and the zona reticulata in response to adrenal corticotropic releasing hormone. The two most common glucocorticoids are cortisol and corticosterone. That's kind of a tongue twister for me. These are two hormones that are going to focus on us digesting fats. They're going to stimulate fat and protein catabolism, the digestion of fats and proteins, and they're also going to focus on upregulating glucose concentrations into our bodies. Why do we need to do this, or why would we need to do this? We would need to do this in a situation where we need to repair proteins in our bodies, or so we need to have more amino acids mobilized into our bodies, and in a situation when we need to have more glucose readily available. So think of stressful situations, that sympathetic activation of the nervous system, the fight or flight response, or think of healing from an injury. The glucocorticoids also have an anti-inflammatory effect. Long-term use of these hormones downregulates the anti-inflammatory effect, but for short-term periods of time, these hormones can make it so that we have less inflammation in the body. But repeated or prolonged exposure to these hormones make it so that our bodies adapt, and then we can no longer have that anti-inflammatory response. As we look at those sex steroids, that are released by the adrenal cortex, in particular the zona fasciculata and the zona reticularis, we have androgens. Androgens, and generally speaking, is a broad category of chemicals that we think of as a broad category of sex hormones, and they include many smaller, many subcategories, including DHEA or progesterone, etc., etc. When we think of androgens, I want you to think of the hormones that set libido, sex drive throughout your lifetime. In particular, when we think of androgens, I want you to think of male sex hormones. So androgens, particularly where a child is exposed to androgens in utero, that child is going to be pushed down the male developmental pathway and will have lots of dehydroepiandrosterone released, or DHEA released into their bodies, and that's going to cause other tissues to convert that DHEA into testosterone. So you can think of this dehydroepiandrosterone as a precursor to testosterone. Another one of the sex hormones is called estradiol. Estradiol is the most potent of the three forms of estrogen. Now, as we look at the amount of estradiol released from the adrenal cortex, it's pretty small, but post-menopause, that estradiol becomes very important for maintaining the woman's skeletal bone mass, or the bone mass of that woman's body. As we look at the tug and pull, or the interdependence of the adrenal glands, we find that the medulla and the cortex are functionally totally independent of each other. They're structurally very close to each other, one wraps around the other, but functionally they do very different things. As we age, our medulla is going to atrophy if we don't have any stimulation from cortisol. As we're looking at the adrenal medulla, some of the chromaffin cells of the medulla will extend upwards into the cortex, and they can stimulate the cortex to release corticosteroids, which are then going to release cortisol that will then stimulate the medulla itself. So the medulla can stimulate the cortex to release the hormones needed to keep the medulla from atrophying or degrading. So that was our crash course on the adrenal gland. The hormones that I really want to emphasize to you are aldosterone and cortisol, and also the androgens, the sex hormones from the adrenal glands. Our adrenal gland has both a cortex and a medulla. And if you have any questions, comments, or concerns, please feel free to post them on the discussion boards or shoot me an email. And as always, happy studies.